So we're going to cover energy and SHM this morning, and we're going to have a look at how the energy changes when we've got a simple harmonic system, and we're going to define some equations to go with that. So let's start off with a really nice system for SHM, and that is going to be the good old pendulum. There's lots of situations where the pendulum's really important, and when we look at the pendulum, there's three positions. Well, there's lots of positions it could be in because it's continuity, but there's three positions where there's something interesting is happening, and we'll call those X, Y, and Z. So as the pendulum goes through, it's going to go to that point, and it's going to come back, and we'll go over my X, Y, and Z, and back to that point. So one whole cycle is going from X to Z and back to X, so it goes through Y twice. Now, the interesting thing about simple harmonic motion and energy is that actually if we had no friction, an object in simple harmonic motion would in fact run forever. There's no losses of energy. It's almost a perfect system in a perfect world. So no friction means that there is going to be no loss of amplitude and no loss of speed. And in that situation, we only have one force acting on the pendulum, and that force is what we defined last time as our restoring force. So depending wherever we are on the cycle, we're always trying to have a force that restores us back to that central point. So let's look at the energy. Now, if we consider that this point here is a height delta H above the zero, which we'll consider this point at the middle of Y, and we can say the same about this end, then because we know we're gaining height, we know there is gravitational potential energy. So we can say that there is a maximum potential energy at the limits X and Z, because that's the point where it's got the greatest above the ground and the same on the other way. So it's got the greatest above the ground in that direction, it's going to swing back to zero where it's quite low to the ground, and then it's going to swing back up and it's going to have the greatest distance from the ground again. Now that means that that energy must be being transferred to something else when it reaches Y. Well, we also know that where there's no acceleration, which is the point in the center, the equilibrium position, we must have maximum speed. So therefore we must have maximum kinetic energy at Y. So if we know that there's no loss of energy, then we can also say that the total energy, ET, is going to be equal. Okay, so that total energy is going to be equal because no matter where we are going to have either gravitational or a mixture of the two, and that's the way this is going to work. So let's draw ourselves a table. It's an important table to know. Let's look at our position, X, Y, and Z, and we'll look at the potential, EP, and we'll look at the kinetic, EK. So at X, the kinetic is zero because it's a turning point. Remember, we've got the maximum restoring force back to the center because that's a function of how far we are away from the equilibrium point. So that means that the total energy at this point here must all be in potential energy. So ET. But there's no kinetic energy because remember, we reach that turning point right at the end, it's got to turn around, so there's a point of zero velocity, which means we've got zero kinetic energy. We can do the same for Z because we know it's just acting in the opposite direction. It's still going to be that the potential is the total energy and the kinetic energy is zero. And when we're at Y, because our restoring force is zero in the center, because we're at that point, there's no acceleration either direction, positive or negative, therefore the kinetic energy now must be the total energy. So we can define those stages as the amount of energy that they have. When we're at x, because we're at a turning point, because the restoring force is the greatest, the acceleration is the greatest, or the deceleration in this case, it means that we're going to have a zero velocity, which means there cannot be any kinetic energy. As we swing into the centre, into this y position, we know that there's no gravitational potential energy because we've got no height above the minimum line, which is this line through the centre of the mass, and that means we must have maximum kinetic energy. So all of my energy that was here has now been transferred into kinetic, so we've changed it from potential to kinetic. And then as we swing back the other way, we can see that the total energy is in fact going to be potential, because again we're at a turning point and there is no velocity at the turning point. So we've got this information relating to our situation where we're looking at a pendulum. Well, that's one type of simple harmonic motion system. Let's look at another one. So we're going to have a look at a spring. So we'll start with a displaced spring. There's my displaced spring with a mass on the bottom. We've got to have a mass to make it oscillate. We'll draw the equilibrium position, because that's where it's going to go to. Put the same mass on. And we'll draw a compressed one, so it's gone above the equilibrium point, and then you can imagine it goes back the other way. And in fact, actually what I want to do is I'll put a few dots and we'll go back to where we were. No, I haven't done that very well. We'll go back to where we were right at the beginning. So that's the mass there. So this time we need to think about where the energy is going to go. So we know there's motion. We know there's motion. We can see there's motion. So the kinetic energy is going to change into a potential energy. And we've got two options for the potential energy. It can either be an elastic potential energy, which comes from the spring, or it can be a gravitational potential energy, which will come GPE, which will come from the height relative to its lowest point. Now we know that the energy is going to change with the displacement. So EP is going to be proportional to x. And in fact, from your GCSEs, you remember, hopefully, that the elastic potential energy is 1/2 k x squared, where k is your spring constant. So the maximum potential energy must be when the displacement is maximum. So when x becomes a, we end up with 1/2 k a squared, where a is the amplitude. So I'm going to have to rub these little bits out the top, so we'll carry on at the top here. If we now talk about the total energy in this system, we can say that the total energy is going to be equal to the potential energy plus the kinetic energy. And we know what the potential energy is because we've dealt with that. And we can define the kinetic energy, so EK, is going to be equal to ET minus EP. So the total energy minus the potential energy is going to give me the kinetic energy. Okay, so we know what the total energy is, we're told. Total energy, we worked out, was going to be 1/2 ka squared. So 1/2 ka squared. And the potential energy, we know is 1/2 kx squared. So minus 1/2 k displacement squared. And if we put this and simplify it, we can say, well, we've got 1/2 k a squared minus x squared. So now we've got an equation for the kinetic energy. So this is the kinetic energy of a spring. Now we can go a step further than this because that's all well and good. It's given as a kinetic energy, but we also know that the kinetic energy is equal to 1/2 mv squared. We learned that in our GCSEs. So we can actually now start to equate these two together. We can say a half k a squared minus x squared, which we worked out is our kinetic energy, is going to be equal to a half mv squared. I think you can see where we're going here. We can define the velocity of our spring in this situation. I can cancel my halves, I know that, and I can equate this to v squared. So I've got k over m lots of a squared minus x squared, so the difference in the amplitude squared minus the displacement squared. We also know that omega squared, this is where it all starts to come back together, is equal to k over m. So everywhere where we've got a k over m, we can now put an omega squared. So therefore I can say it's omega squared lots of a squared minus x squared is equal to v squared. Well, we can also simplify this just a step further, because we can now say, well, the square root of v squared gives us v, and that is going to give us plus or minus, and the plus or minus here is really important, because remember, when you've got a squared situation, you have two answers. If we draw a squared graph in terms of maths, it's going to look something like that, and if my answer could be there or there, if that's what I'm trying to get to, then I've got a plus or a minus. So therefore I need to have this plus or minus omega, and it'll be plus or minus omega square root of a squared minus x squared. So we've now defined what the velocity is in our spring. So at any point in the spring, we can work out, if we know the omega and we know our amplitude and our displacement at that time, we can know how fast our object is moving. And we can do a situation. So if x equals 0, then we can make our situation simpler. Because if x is 0, remember, we're going through the centre, the equilibrium point of our spring. So we can say that v is going to be equal to plus or minus omega square root of a squared, and because we've got 0, we can lose that x part, and the square root of a squared is in fact just a. So the maximum velocity, so v max in this situation, is going to be omega times a, and that's my maximum speed, which is going to happen when it passes through that equilibrium point. So when the spring is bouncing down and it passes through the equilibrium point, remember the restoring force is 0, so my deceleration in either direction is 0, so therefore my velocity must be the maximum. Okay, so that's quite an important aspect, and that now allows us to calculate the maximum speed and the speed at any point during a cycle. So let's now go a step further and let's think about what these graphs would look like. So, energy displacement graphs. And along the y-axis, we're going to have the total energy. In fact, we're not. We're going to have energy. My apologies. We're not going to have total energy. We're going to have energy. So along the y-axis, we're going to have energy, and along the x-axis, we'll have plus a, and we'll have minus a, because this is obviously the displacement. And we'll call that x, and obviously in the centre we've got 0, so 0 being our equilibrium position. And that is going to be what we'll write here. So the equilibrium position is at 0, and then we've got our maximums and our minimums. Okay, 3 different colours here. It's quite helpful if you've got it. I've got 2. I'll have to use blue again, but let's go with red first, and we'll go with kinetic first. Let's go with EK. So kinetic energy. The kinetic energy when I'm at either position, minus a or plus a, Well, let's put it into our equation. Let's go back to that value for V, because we know that whatever V is going to be proportional to our kinetic energy. So V was equal to plus or minus omega root a squared minus x squared. If we think we're at plus a, well, plus a squared means I've got a squared minus a squared, which is going to be 0. So if x is a, then V is going to be 0. What about if x is minus a? Well, if x is minus a, then I'm still going to end up with minus a squared, sorry, for my x, and minus a squared is going to be a squared. So I've got a squared minus a squared, so V is going to tend to 0. And if V tends to 0 in those two situations, then we also know that EK is going to be 0 and EK is going to be 0. Okay, so let's put our little points on our graph. We know those two situations are going to happen. What about when x is 0? We did this a moment ago. If x is 0, then we're going to have the velocity as being omega a, which is the biggest number you can possibly get out of this. Depending upon what omega and a is the size of the number, but that's the biggest value you can get for this situation. So therefore, the energy when we're passing through the centre, through the equilibrium point, is going to be at a max. So EK in this situation is going to actually be equal to ET, the total energy. How does it change as we're moving from minus a to a? Well, it's not going to be a straight line, is it? Because we've got an a squared minus an x squared here in terms of V, and we know it's V squared in the first place for half mv squared. So therefore, it's got to be a nice squared graph, inverse squared graph. That was terrible. I'm sure you guys can do better when you join us at home. But we've got a nice inverse squared graph. Okay, what about potential energy, EP? Well, we know that when we're at plus a or minus a, we've actually got the maximum change in height. If we have the maximum change in height, then we must have the total energy at either point. So therefore, when we're at plus a, we're going to have ET, and when we're at minus a, we're going to have ET. What about at 0? Well, when we're passing through 0, we're going to have 0. And in fact, they're going to look like that. So one is a negative x squared curve, and one is a positive x squared curve. Those are our relationships that we're looking at. So what about if I take each step? It kind of looks like these two are out of phase. Well, if I add 0 and the total together, I get the total. If I add half of the kinetic and half of the potential, I'm going to end up with the total. If I have EK being maximum and EP being minimum, I'm getting the total. So hopefully you see you're going to get a straight line through, where that straight line is in fact the total energy. So the summation of my kinetic energy and my potential energy is going to give me the total energy, which is what we kind of started with. So we're saying that ET is equal to EP plus EK. And in any point in this situation when we're in simple harmonic motion, these two things added together gives us the total energy. And that means that we can go one step further, because we can actually say we know what the total energy is. It's a half Ka squared. So therefore we can say a half Ka squared is equal to EP plus EK. And that gives us a starting point for any of our calculations that we need to work from. So remember, potential energy is at a maximum when we're at the maximum displacement from the central point, from the 0 point, and is also at a maximum when we're at the negative one, so positive and negative, so we end up with that nice curve. Kinetic energy is at a minimum at either of the turning points because we have no velocity, because remember that the turning force is going to be the greatest, so the acceleration is going to be the greatest negative direction, therefore it's going to slow down till it stops. And when it passes through the centre, the kinetic energy is going to be the greatest because we have no restoring force, so therefore there's no acceleration, so we're going to hit the greatest speed. So we get the same in the inverse direction. Let's look at this in a simulation, because I think that will start to make a bit more sense as we do it. So moving over to the Phet simulation, we have got the energy graph here. We can see kinetic energy, potential energy gravitational, potential energy elastic. We've added those two together. There's a thermal energy, which we're going to remove for the moment, and we'll talk about that in a moment. And there is a total energy. So I'm going to slow this down so that we can look at it very closely. As I displace my spring, let's look at the way the energy is moving. So you can see at this moment in time, the total energy is the gravitational energy, potential energy, plus the elastic potential energy. Because we have still gone above the height we're at. In fact, I could pull it to the height and we'd see there's no gravitational potential energy, or zero if we go there, and it's in fact all elastic potential energy. But it doesn't matter for us because we're considering the potentials as together. So we'll start a bit higher up. When I let go, the kinetic energy gains and then drops, and gains and drops. And why is that? Because it's passing through that equilibrium point. Check the equilibrium point. As it passes through, the kinetic energy is at its maximum. And we can see that the total energy here is made up of all three of those points together, ensuring that our total energy is known. But what happens if we add some friction? Because this is great in an ideal situation, but it's no good if we wanted to actually model what's going on in real life. The kind of frictions we're talking about here is we're talking about air resistance. We're talking about the friction between the pendulum string and the support that it's moving on. We're talking about all sorts of frictions that are taking place. And in fact, when we're adding those frictions in, what we're actually doing is adding a loss through the thermal energy. So I'm going to do that by adding a very small amount of what we call damping, and we'll talk about that in a moment. But you can see that the thermal energy is building, and what is happening to the oscillation, what is happening to how far it is managing to oscillate to and from. Let's put this down here somewhere so you can see, so it's roughly about there. So over time, we should see that this oscillation is getting smaller, because we're removing some of the energy from that system. And as we remove the energy from that system, we can also see the kinetic energy is dropping, and so is the gravitational potential energy, and so is the elastic energy. Because that energy is being dissipated into the surroundings. Leave it long enough, what's going to happen? Our spring is going to return to that mass equilibrium line, because that's where it's going to be when it has no remaining energy left, or no energy left in comparison with what it had to start off with. So in this situation, we can see we're losing it through the thermal energy, and pretty much there, it's not doing any more, it's not bouncing up and down anymore very much. It's just oscillating around the equilibrium line because we've lost a huge amount of energy into the surroundings through thermal. So we'll just go back to the visualizer, because now we need to talk about let's go back to that one, about what the different damping situations are. So we're losing the energy into the surroundings. That's really, really important. And that's what's causing our amplitude to decrease. So any of the energy we're losing goes into the surroundings, is lost as thermal energy, and we call the forces that are doing that dissipative forces. So they are dissipating the energy that was in the system. And remember that everything really wants to go to zero energy. That's kind of a law of physics. It wants to lose that excess energy it has and remain at its equilibrium position. Because if it has too much energy, it's going to move. And in our situation with a simple harmonic oscillator, it's going to move back to the equilibrium position. And we call these damping forces. And there's three types of damping that we're going to cover in diagrams now. We've got light, we've got critical, and we've got heavy. And these damping forces are really important. They're important to make sure that when something is oscillating in simple harmonic motion, it doesn't just keep oscillating. You wouldn't want to be sat in your car going over some bumps. So here's your bumps, and you're in your car, and the spring is extended. It's a pretty complicated system, but the spring is extended. I might have exaggerated a little bit. But as that spring is extended and you move back onto a flat surface, you don't want that car to be oscillating up and down for the next 10 minutes because it's gone over a bump. So you want to remove that energy from the situation, and you do that through having the damping of the forces. You damp that oscillation to ensure that any energy that's been removed from it is causing it to return to where it wants to be. Okay, so 3 damping situations. Let's talk about light first. If you have light damping, then this is what the oscillations look like over time. So there's time, and there's our displacement. And we'll start by having displaced it. So it's going to oscillate down. And actually, I need to just put in what we'd call a damping envelope. And you don't really need to know that term, but it's a proper physics term because that allows us to get this damping looking correct. Because the oscillations are going to get smaller and smaller and smaller until you're back to that equilibrium position, you're back to that 0 position. And it's going to do that over time, but what's really important to note is the frequency remains constant. So the time period is independent of the amplitude. So it doesn't matter how big the amplitude is, you've still got the same time period, you're still at the same frequency. But the oscillations are dying away. And why are they dying away? They're dying away because you're losing energy into the surroundings. The energy that you did have at the peak at this point here is less at this point, which is less at this point, etc., because you're losing that difference in energy. And obviously this isn't an energy time graph, but we could make it an energy time graph. But you're losing that energy over time into the surroundings. But it's taking a long time for that to damp back to 0. So if this was used in your car, you would still feel the car moving up and down, up and down, up and down, until eventually it stops oscillating. So not a good system to use if you're talking about damping suspension. So let's have a look at another one. Critical damping. Now when we've got critical damping, we've got a much more complex damping system taking place. We have moved our, in fact let's use 2 colours here, so if I put on, so on our previous oscillation we were oscillating with a frequency roughly like that, so those little red dots are our oscillating frequency, and in fact let's just put one in so we can see they're coming down, it's getting smaller, but it's still got the same time period between them. In critical damping, it follows the same process and just becomes flat. There's no overshoot. So you go onto the bump and you return back to where you were at 0. There'd be no bouncing up and down, there'd be no way the car's moving up and down. You would just move down as you enter the bump and then move back to 0, and that would be it. That would be the oscillation. So critical damping is that the oscillations are stopped. So the oscillations stop after being released. So you don't get any more oscillations than just that first one. In fact, let me draw this again so you can see it just slightly better. That's it, that's all it does, and it stays flat, it goes to 0. It returns to the equilibrium point that just means equilibrium, by the way. So it returns to the equilibrium point in the shortest time. Okay, so the shortest possible time. And where would we use that? Well, that would be an ideal situation for car suspension. If you've got critical damping, you're not going to feel the road particularly much, because as you go down a bump, you'll come back up again and you won't feel any oscillation on top of it. So it's great for car suspension. And that's a good situation to use it in. So we've got the third one. And the third one is where we have got heavy damping. Now, heavy and light, there's not massive difference between them. It's about how quickly it returns to zero and how many oscillations will happen. So if we're looking at heavy damping, then again, we have the same damping envelope, but it might be a bit of a steeper gradient. So it's going to return back to zero in a shorter time. So let's draw it on. We're going to have one oscillation, back up, 2, back up, 3, and then we're effectively 0. So the damping is so strong the time to return to x0, so the time to return to the equilibrium, is longer than critical. So that actually means we put too much force into it. Okay, so this is, if we do a force continuum on here, we can say, well, we've got low to very high. So actually you don't need to have the most force to get critical damping, you need to have the right force, and that will come out in the next lesson. Oh, I am so sorry, I've drawn heavy wrong. Ugh, that was not what I wanted to draw. My bad. Right, so heavy, have another go at that. I will cut that out in the video so I don't get that wrong. But heavy looks like that. It looks like the damping envelope. So damping is so strong that the time to return to equilibrium is longer than the critical time, and there is no oscillation. So you don't go below the 0 point. It doesn't oscillate upwards and downwards. It stays in that simple system, or simple idea here, of returning to 0, but it hasn't returned to 0 as quickly, so we draw that on, as critical, which would be the red line. So that would be critical, and that would be heavy. And we'll not put light on there because it becomes too complex. So when might we see a situation like this? Well, if we had a spring and a mass, and we would do this in the lab. So this is an experiment we could do, and we had a very high viscosity material inside of our container, then we'd find that this takes longer to return to 0, but no longer has the energy, because it's lost it to the dissipative forces, it's lost it in doing work, in trying to return to 0, to actually oscillate above. So this would very, very slowly move back up to the 0 point, which potentially might be on the surface, and in doing so, there's no way it's going to oscillate. It's had to use enough energy just to get it back to the 0 point. And that is a heavy damping, and obviously critical damping is what we would see in the car suspension.